We're now going to go over matter maps. This is something that you'll frequently see on tests. They give you a chance to show your understanding of the structure of matter, to visualize the structure of matter, visualize the smallest particles of the substances that you are studying. Matter maps have some definite limitations. They're only models of what things look like submicroscopically, below the limit of our ability to actually see anything even with the best instruments. When you see gas particles, like the ones you see on the screen now, they are way too close together. Real gas particles are much, much farther apart, and they're moving, of course, very, very fast. And when you draw a matter map of a solid or a liquid, you can't show that they're actually vibrating because they have kinetic energy, the energy of movement. Let's look at an example and you'll see how useful matter maps can be. What would you think that this would be? A solid, a liquid, or a gas? Well, the particles are very, very close together, so they can't be a gas. They are packed very, very regularly, so they really can't be a liquid. And of course, they're all at the bottom of the container, not scattered throughout. So they must represent a solid. This diagram is a matter map of a solid. Regularly packed particles, all at the bottom. Now, the second question, is this pure element, pure compound, or some kind of mixture? Well, from your understanding of elements, compounds, and mixtures, you should be able to answer that. All the particles look alike, so it's pure. And there's only one kind of particle. They all look the same. And that means it has to be representational of an element. This is a pure element, and it's a solid. In reality, what we're showing in a matter map is a snapshot of what the particles would look like if we could see them and if they were standing completely still. What we show in a matter map, this snapshot, is really a picture of what it would look like at a given instant. All solids, liquids, and gases have some kinetic energy. So the particles are actually vibrating around their positions. Now, what does a gas look like? Well, the particles are very far apart, and they're not settled on the bottom of the drawing. And of course, they're moving, and we can't see that. This is a snapshot. We'll do experiments in the lab in this next unit to get a better idea of what gas particles actually do in nature. What does a liquid look like? Well, the particles are close together like solids, but they're not regularly packed together like a solid. Their potential energy is different because they're able to slide around each other. This diagram, too, is just a snapshot. Liquid particles are in constant random motion, but unlike solid particles, they're not in motion around a certain point. They can move past each other. That's why, as gases are, liquids are fluids. They can flow. Now, what does a compound look like? So far, we've been looking at pure elements. Compounds would be made of two or more different elements put together in a consistent manner. We say with a definite proportion. So in this case, we have three little atoms bonded to one big purple atom, and we have three of these smallest particles of a compound. It has to be a compound because we have more than one kind of element, and they're always in the same 1:3 ratio. Now, with this, again, the same compound, would it be a solid, liquid, or gas? It's a gas. The particles are quite far apart. Now remember, in reality, they would be a lot farther apart than could fit three on this diagram. They'd be maybe 1,000 or more diameters apart as a gas. So if you could see one at all in this diagram, there'd only be one there. What does a mixture look like? Well, a mixture is made up of two or more different substances. They can be elements, they can be compounds. So you'll see differences in the particles, and they're going to be separated from each other. Perhaps, like here, they're separated in a kind of a gas situation, kind of haphazardly. Perhaps this would even be a homogeneous mixture, or they could be layered, in which case you'd see a heterogeneous mixture. These are, of course, representations of gases mixed together. A mixture of a gaseous element and a gaseous compound. How about a liquid mixture? Well, we're going to show the elements or compounds to be close together, not spaced around the whole volume. They'll be kind of haphazardly placed together. This is, of course, a mixture of a liquid element and a liquid compound. And if we did it perfectly, they'd all be down towards the bottom of the container. Is this a homogeneous mixture? Well, it appears to be homogeneous. It looks like a mixture of a liquid element and a liquid compound that is well mixed. There don't seem to be any layers here. There's not two phases. All right, let's do some practice. We'll just give you a few moments to look and see. Are we looking at element, compound, or mixture in each one of these diagrams? Here's our second practice. Here's our third practice. Here's our fourth practice. And here's our fifth practice. Okay, we're going to go back to and go over these. The first practice, you can see up here, widely separated, therefore it looks like a gas. You can see that compound that we were looking at earlier. And it's a gas. But here we have that solid, all the same, all packed together regularly. So this is, I guess you'd call it a mixture of a gas sitting on top of a solid element. Gaseous compound over solid element. Here we clearly have an element. Every one of these is exactly the same as every other one. And it looks like we have a gas of the element and a liquid of the element. This could be, for instance, if we had liquefied xenon, real cold, with some of the xenon gas on top of it, that would be something that we would say is a gaseous element over a liquid of the same element. Our practice 3, here's a gas and it's an element. This is clearly a liquid and it's an element, and here is a different element in the liquid phase. So we have really 3 phases here: the gas, the liquid of the same element, and then a liquid of a different element below. You might ask, which of these is less dense than the other, because the liquids are floating on top of each other? Our fourth practice, well, that's fairly complex. Let's see if we can identify what's in here. Well, first of all, we have a gaseous element. These red with the little white stars in the middle would be a gaseous element. Here's a different gaseous element here that's kind of purple with yellow shiny things in the middle. So again, it's a mixture of these two gaseous elements, but there's also, notice, different atoms bonded together in a definite one-to-one proportion. This must be a gaseous compound. So this is a gaseous mixture of two elements, two elements, and one gaseous compound, homogeneous mixture. In 5, this is an interesting one because we obviously have liquid. It's kind of haphazard, but it's all at the bottom. There seems to be no vapor above it, so it's a low vapor pressure liquid. But there's another liquid mixed in with it. These are different colors, so that seems to represent a different element. So these are two liquid elements, yet they are mixable, or miscible as we say in chemistry. And this would be our 5th and last practice.